What if I told you that you're not actually the same person you were a few years ago? Or that a perfectly simple sentence could literally break logic? Well, today, we're going to dive into some of the most fascinating paradoxes ever dreamed up, ideas that really push our whole understanding of reality right to the edge.
So let's just start with a question that hits pretty close to home. I want you to think back to who you were, say, 5 or 10 years ago. Do you feel like the same person? You probably think, yeah, of course. But on a purely physical level, you're basically a complete stranger to your past self.
You see, your body is in this constant state of renewal. It's kind of wild. As you're just living your life, there's this invisible, microscopic construction crew inside you that's always at work, swapping out old cells for brand new ones. And over several years, this process is so thorough that almost every single atom that made you, has been replaced.
Okay, so if the actual stuff you're made of has been completely switched out, what is it that makes you, you? Is it your memories, your personality? This very question, this puzzle of identity over time, well, it brings us right to our first huge paradox.
This exact problem was tackled by ancient philosophers through a brilliant thought experiment about a legendary ship. It's called the Ship of Theseus, and it perfectly captures this puzzle of what makes something stay the same thing when all its parts have changed.
So, here's how it goes. Imagine the famous ship of the Greek hero Theseus is being preserved as a historical artifact. As the old wooden planks start to rot away, they get replaced, one by one, with brand new identical planks. And this goes on for years, until eventually not a single original piece of wood is left. So, is the ship floating in the harbor still the real Ship of Theseus? Most of us would probably say, yeah, sure.
But wait, here's where it gets really weird. Let's say the person in charge saved all those old original planks that were removed, and over in another part of the harbor, they've painstakingly put them all back together again, reassembling the original ship.
So now you have two ships. Ship A is the one that's been continuously maintained, but it's made of entirely new material. And then you have Ship B, which is built from every single one of the original pieces. So which one is the actual Ship of Theseus?
Philosophers have been arguing about this for centuries. You could say Ship A is the real one because an object's identity survives that gradual change. Or you could argue that Ship B is the real one because an object is nothing more than the sum of its original parts. Or, hey, maybe the answer is that it's just confusing. Maybe they're both the ship. Or maybe the whole idea of the original ship just doesn't mean anything anymore.
So the Ship of Theseus messes with our ideas about physical objects. But what happens when the very language we use to think about the world turns in on itself and gets twisted up? Let's take a look at what happens when logic ties itself in knots.
Okay, picture this. It's a simple little town. And in this town, there's one barber who has a very specific rule. He shaves all the men in town who do not shave themselves, and only those men. Seems straightforward enough, right?
But then, we have to ask the critical question, who shaves the barber? Think about it. If he shaves himself, he's breaking his own rule, because he's only supposed to shave guys who don't shave themselves. But if he doesn't shave himself, then according to his rule, he has to shave himself. He's completely trapped in a logical contradiction.
Now, this isn't just a fun little brain teaser. This same kind of logical trap was discovered deep in the heart of mathematics by the philosopher Bertrand Russell. And his discovery, Russell's paradox, sent absolute shockwaves through the math world. It challenged the very foundation of set theory, which was the system they were using to build everything else. It totally devastated pioneers like Gottlob Frege, who felt his life's work was suddenly built on sand. So here's the basic idea. In math, you have these collections of things called sets. You can have a set of all dogs, for example. Easy. But you can also have sets that contain other sets. So Russell came up with a very special kind of set. Let's call it S. The rule for S is that it contains every set that does not contain itself as a member. And this brings us right back to the barber. We have to ask the question, does this special set S contain itself? Well, if it does contain itself, then by its own rule, it shouldn't be in there. But if it doesn't contain itself, then it meets the criteria to join the set, so it should be in there. It's a complete, mind-breaking contradiction at the core of logic. Okay, one more of these self-reference puzzles, this time just with words. We can split adjectives into two groups. Some are autological, meaning the word describes itself. For example, the word English is, in fact, an English word. Then you have heterological words, which don't describe themselves, like the word German is not a German word, right? So, here's the zinger. What about the word heterological itself? Is it heterological? Well,
If it is heterological, that means it describes itself, which would actually make it autological. But if it's autological, that means it doesn't describe itself, which would make it heterological. Again, our own language just ties itself into an impossible knot.
All right, so we've seen logic and language create these impossible loops. But what about the physical world we actually live in? The ancient Greek philosopher Zeno argued that, if you think about it logically, something as simple as moving from point A to point B should be totally impossible.
Imagine you want to run a 1-kilometer race. Seems simple, but Zeno points out that before you can finish the race, you have to get halfway there, right? To the half-kilometer mark. And before you can get to that point, you have to get halfway to the halfway point, a 1/4 kilometer. And before that, an 1/8, and then a 1/16, and so on forever.
You see the problem? Any distance can be divided in half, an infinite number of times. So to get from the start to the finish line, you have to complete an infinite number of smaller tasks. And completing an infinite number of tasks seems like it should take an infinite amount of time. So how does anyone ever finish a race?
Now, this one is pretty cool because mathematics actually gives us a way out. We now know that you can add up an infinite series of numbers and have it equal a finite normal number. It's a concept called convergence. And it turns out that 1/2 plus 1/4 plus 1/8 and on forever adds up perfectly to exactly 1.
Modern physics gives us another possible answer, too. It suggests that there might be a fundamental limit to how small you can divide space. This teeniest possible distance is called the Planck length. And if space can't be divided forever, then Zeno's paradox just kind of disappears. There's no infinite number of steps to take.
So, we've journeyed through these bizarre thought experiments. Ships that might not be what they seem, barbers who can't exist, and races you can't logically finish. What's the point of all this? What could these puzzles actually teach us?
The real value of a paradox isn't about finding the clever gotcha answer. It's about what happens when our most trusted tools for understanding the world, our own intuition, our language, even the basic rules of logic, start to wobble and break down. They force us to stop and question the fundamental things we just assume are true.
These paradox shows show us the cracks in the foundation of our reality. They prove that what seems obvious on the surface can become unbelievably contradictory when you look closer. So I'll leave you with this final thought. If our best tools for making sense of the universe can fail so spectacularly, what can we ever really truly know for certain? It's something to think about.